In this video, we're going to be talking about the nomenclature of inorganic complexes. We will be discussing how to name ligands, metals, metal-ligand complexes, as well as how to write chemical formulas for these metal-ligand complexes. Before we begin, I would like to address a few changes in the current rules of naming complexes. I'm not entirely sure when these changes were made, but in the most current version of the Red Book, there are a few things that are slightly different from what most of us are familiar with. Most of the resources online still follow the old conventions because they've been around for a very long time. So if there's any inconsistency with the content of this video versus what's in your textbook or what's in other online resources out there, it's only because we're using the most recent set of rules. There are three major differences between the current way and the old way of naming complexes. The first change is in the naming of anionic ligands ending in an IDE. In the old convention, the IDE is replaced with an O, so chloride becomes chloro, cyanide becomes cyano, and hydroxide becomes hydroxo. But in the current system, the IDE is replaced with an IDO, so chloride becomes chlorido, cyanide becomes cyanido, and hydroxide becomes hydroxido. It's a minor change, but it makes the naming more consistent, with ATE becoming ATO or ITE becoming ITO, because now IDE becomes IDO. The second change is for ligands which are ambidentate. In the old rules, you would specify which atom is coordinated to a metal by putting a dash followed by the letter of the coordinated element. For example, thiocyanate ligand coordinated through an N will be named thiocyanito-N. In the new rules, you have to include the Greek letter kappa before the letter of the donor atom. So instead of thiocyaneto-N, it becomes thiocyaneto-kappa-N. The third change concerns the sequencing of ligands in writing a chemical formula for the complex. In the old system, you have to list down the ligands alphabetically, but you also have to cluster the anionic ligands and write them first, followed by the neutral ligands. In the new system, you just list the ligands in alphabetical order regardless of charge. So these are the three major changes in the naming of complexes, and if you're familiar with the nomenclature of inorganic complexes already, you just have to keep these changes in mind when you do so in the future. So now we begin the actual lecture on naming complexes. The first step in naming a complex is knowing how to name the ligands. Ligands, as you should already know, are Lewis bases and therefore will act as electron pair donors. Since they donate electrons, they will usually either be negatively charged or neutral and never positively charged. So considering these two categories of ligands, let's see how naming conventions are different for anionic ligands versus neutral ligands. Anionic ligands will usually have a suffix of "ide", "ate", or "ite". In our examples, we have chloride, hydroxide, sulfite, sulfate, oxalate, acetate, and ethylene diamine tetraacetate. When naming these anions as ligands, we simply change the E in the end to an O. So an IDE becomes an IDO, an ATE becomes an ATO, and an ITE becomes an ITO. In our examples here, Cl-, which we will name chloride when it is in solution, is changed to a chlorido when it is coordinated to a metal. We change the IDE to an IDO. In the same way, the CH3COO- anion, which is named acetate when in solution, becomes acetato when coordinated to a metal. We change the ATE to an ATO. So that's how you name anions as ligands. You just change the E in the end to an O, and you have a name for your anion as a ligand. Next, you have neutral ligands, which are much more simple to name. The name of the ligand will usually just be the name of the actual compound. In our examples here, we have the compound CH3NH2, which is called methylamine. When you put it in a complex and coordinate it to a metal, it is still called methylamine. So the same is true for the other neutral ligands such as pyridine, trimethylphosphine, and 1,10-phenanthroline. When you name them in a complex, you just use the actual name of the compound. There are, however, 4 notable exceptions to this rule. The compound ammonia, for example, is named amine when coordinated to a metal. That is amine spelled with a double M. The double M distinguishes ammonia as a ligand from other amine derivatives. This makes the complex name unambiguous. The second exception is the compound H2O, which we all know as water. When coordinated to a metal, it is named aqua. Then we have carbon monoxide and nitrogen monoxide, which are named carbonyl and nitrosyl respectively. Lastly, for ambidentate ligands, we will need to specify which atom is coordinated to the metal. Ambidentate ligands are special ligands which can coordinate through several different atoms. From our examples here, we have the ligand NO2, which can coordinate either through the N or through the O. Since it is an anionic ligand, we will follow the convention for anionic ligands and call it nitrito. But since it is ambidentate, we will also have to specify the atom which is directly connected to the metal. We do this by adding a dash, followed by a kappa, followed by the symbol of the coordinated element after the name of the ligand. So a nitrito coordinated through N is called nitrito kappa N, and a nitrito coordinated through O is called nitrito kappa O. And that does it for the names of the ligands. To summarize, neutral ligands will just retain their names, save for the 4 exceptions that we specified previously. For anionic ligands, you have to change the last letter from an E to an O. And if the ligand is ambidentate, you have to specify the atom which is connected by adding a kappa followed by the symbol of the coordinated element. Now that we know how to name the ligands, we will learn how to specify how many of each ligand is present. To denote the number of each ligand, we will use the Greek prefixes di, tri, tetra, penta, and hexa to denote 2, 3, 4, 5, and 6 ligands respectively. So, if we have 2 Br- connected to a metal, in the complex name, you write dibromido. If you have 4, you write tetrabromido. If you have 6, you write hexabromido. Usually, if there's only one ligand, the prefix mono is disregarded. So, instead of writing monobromido for a single bromide, you just write bromido. These prefixes only apply to unidentate ligands. Unidentate means single tooth, and it refers to ligands which bind to the metal using a single coordination site. For polydentate ligands, we use the prefixes bis, tris, tetrakis, pentakis, and hexakis to denote 2, 3, 4, 5, and 6 respectively. So, if our complex has, for example, 2 ethylene diamine ligands, the complex name will be called bis-ethylene diamine instead of diethylene diamine. This is done to make the name unambiguous, because if you write diethylene diamine, it can be mistaken for a single ligand that has 2 ethylenes and 2 amines. This is because the prefix di also means something in organic nomenclature. But if you write bis-ethylene diamine, it is easy to clearly interpret it as 2 ethylene diamine ligands. The polydentate ligand prefixes are also used if the ligand name begins with a Greek prefix already. For example, we say tris-trimethylphosphine instead of tri-trimethylphosphine. Care must also be taken in the situations when the use of a multiplicative prefix may be misinterpreted. For example, we use tris-iodido for 3I- anions because triiodido means a single I3- anion. At the same time, we use bisphosphato for 2PO4 anions because diphosphato means a single P2O7 anion. So in summary, when naming ligands in a complex, we specify the number of ligands using Greek prefixes. We use a different set of prefixes for monodentate ligands and polydentate ligands, and we use the polydentate set for the special cases to remove ambiguity. After naming the ligands, we will now talk about naming metals. The name of the metal will depend on whether the complex is anionic, cationic, or neutral. You can determine the charge of the complex by adding up the charges of the metal and all of the ligands. If there is more negative charges, the complex will be net anionic. If there's more positive charges, the complex will be net cationic, and if the charges are equal, the complex will be net neutral. In naming the metal for a neutral or cationic complex, we just use the name of the metal as is. We write the charge of the metal in Roman numerals inside the parentheses and place it after the name of the metal. So, in the complex CuNH342+, you name the metal copper 2, and the name of the complex will be tetraamine copper 2. If the complex is anionic, then the name of the metal is given the suffix ate. So, copper becomes cuprate, silver becomes argentate, and gold becomes aurate. We use the Latin names from which the elemental symbol of the metal is derived and give it the suffix ate. After the metal name, we also place the charge of the metal using Roman numerals inside the parentheses. So, in the complex AuCl4-1, we name the metal aurate 3, and the complex is named as tetrachlorido aurate 3. Now that we know how to name ligands and metals, we can now proceed to naming actual complexes. In naming coordination compounds, we use the same rules as in naming ionic compounds. So the compound name will have two words, the cation name followed by the anion name. If your compound is neutral, then the name will only have one word, which is the name of the neutral complex. In naming the actual complexes themselves, we construct the name by naming the ligands followed by naming the metal. If there is more than one ligand, the ligands are arranged in alphabetical order. Prefixes which specify the number of each ligand is not considered in alphabetizing. So, dibromido will come before chlorido because we consider the B in bromido rather than the D in di. However, prefixes that are part of the actual name of the ligand are considered when alphabetizing. So, for example, the T in trimethylphosphine is considered when deciding alphabetical order. You consider the first letter of the prefix if it is part of the name and it is not just specifying the number of ligands attached to the metal. So to repeat, you name a compound by naming the cation followed by the anion. If the cation is a complex, you name it by listing the ligands in alphabetical order, followed by the name of the metal, followed by the charge. If the anion is a complex, then you name it by listing the ligands in alphabetical order, followed by the name of the metal with the suffix ate, followed by the charge. When deciding the alphabetical order for the ligands, you do not include the Greek prefixes if they are denoting the number of ligands. But if the Greek prefix is part of the actual ligand name itself, you include it in deciding the alphabetical order. The best way to demonstrate what we have discussed so far would be to try to do a couple of examples. If you would like to work on these yourself, you may pause the video now and unpause once you have named the 5 compounds. The first example has a complex cation and a normal anion. So in naming this compound, we will name the cation using the rules of naming complexes, and we will name the anion nitrate. The cation has 4 ammonia ligands and 2 water ligands. We name the ammonia ligands amine with a double M, and the water ligands as aqua. The AM in amine comes before the AQ in aqua, so the tetraamine comes before the diaqua, even though diaqua starts with a D and tetraamine starts with a T. So we do not consider the prefixes tetra and di in considering alphabetical order. Ammonia and water are both neutral ligands, so we can get the charge of nickel by looking at the charge of nitrate. Nitrate has a charge of -1, so the 2 nitrates will have a charge of -2. So to get a neutral compound, the nickel has to have a charge of +2. So 4 amines is tetraamine, the 2 aquas are diaqua, and the nickel has a charge of +2, so we will name the complex cation as tetraamine diaqua nickel 2. The anion is nitrate, so the complete name of the compound is tetraamine diaqua nickel 2 nitrate. In our second example, we have a complex cation and a normal anion. The ligands on the complex cation are thiocyanate, kappa S, and pentaamine. In alphabetical order, we will write the pentaamine first because the A in amine comes before the T in thiocyanate, kappa S. SCN has a charge of -1, and the 2 Cls also have a charge of -1 each. So the 3 ions together have a charge of -3. To get a neutral compound, cobalt should have a charge of +3. Putting it all together, the name of the compound is pentaamine thiocyanate, kappa S, cobalt 3 chloride. The next example is a neutral complex, so the name will only have one word. It has 5 carbonyl ligands, so it's pentacarbonyl, and an iron with a charge of 0, because the carbonyls are neutral, and the entire thing is neutral, therefore iron will also have to be neutral. So the name of the complex is simply pentacarbonyl iron 0. In example 4, we now have a normal cation, sodium, and a complex anion. The ligands in the complex anion are ethylene diamine and oxalate. These are both polydentate ligands, so we will use the second set of prefixes to name them. Since there's only one ethylene diamine, we will just name it simply ethylene diamine. But for the 2 oxalates, we will name it bisoxalato. In alphabetical order, ethylene diamine comes before bisoxalato, even though ethylene diamine starts with an E and bisoxalato starts with a B. Bis is not included in the alphabetical order because we do not include the Greek prefixes when they denote the number of ligands. To get the charge of iron in this complex, we once again have to get the total negative charges and compare them to the total positive charges. Here we have two negatively charged ligands oxalate, which each have a charge of -2. So our total negative charge is -4. To get a neutral compound, the total positive charges should also be +4. Since we already have two sodium ions, the charge on the iron should be +2. So finally, to name the compound, we will have to name the cation and anion. The cation is named sodium, and the anion is a complex, so we will have to use the suffix ate. The full name of the compound is sodium ethylene diamine bisoxalato-ferrate 2. The last example has both a complex cation and a complex anion. The ligands on the cation are diamine, and the ligands on the anion are dicyanide. If we add up the total negative charges and the total positive charges, we will get a +1 charge on each silver. The total negative charges are -2 because there are two cyanide anions which have a charge of -1 each. So if we divide the charge of -2 over the two silver ions, each silver should have a charge of +1. To name the compound, we will have to name the cation and the anion. To name the anion, we will have to use the suffix ate along with the Latin name of silver. So the full name of the compound is diamine silver 1 dicyanide argentate 1. So that is it for our first set of examples. To summarize how we name these compounds, we named the cations followed by the anions. To name complexes, we listed the ligands in alphabetical order, followed by the name of the metal, followed by the charge. If the complex was anionic, we used the suffix ate and used the Latin name of the metal. And for determining the alphabetical order of the ligands, we do not include the first letters of the Greek prefixes if they denoted the number of ligands present. Now we move on to writing the chemical formulas of coordination compounds. We write these formulas in the same way that we write ionic compounds, where we write the symbols of the cations and the anions with no spaces in between. If the ions are complexes, we enclose the complexes inside square brackets. Inside the brackets, you write the symbol of the metal first, followed by the abbreviated names or the chemical formulas of the ligands. Some ligands have complicated chemical formulas, so for simplicity, we use abbreviated symbols to represent them in the formulas of the complexes. For example, instead of using C2O4 for oxalato, we just use the symbol OX. Or instead of using PC6H53, we just use PPH3 for triphenylphosphine. If we're using these abbreviations, or if we have ligands which have more than one atom, we enclose the symbol of the ligand in a parenthesis to separate them from the other ligands in the complex. So, for a chloride or a bromide ligand, we can just use the symbol Cl or Br, but for a hydroxide or an oxalate ligand, we have to put the OH or the OX inside parentheses. Just like in writing the names of the compounds, when writing the chemical formula, we also list the ligands in alphabetical order. We use the first letter of the symbol or abbreviation that we use to represent the ligands to determine this alphabetical order. Whenever possible, we use the donor atom as the first letter in the formula. So for water, instead of writing H2O in the formula, we write OH2 to represent that O is directly connected to the metal. Thus, in alphabetical order, we consider O to be the first letter and not H. Just like in ionic compounds, we use subscripts to represent the number of ligands. If we have two or more ligands, we put a subscript after the symbol of the ligand to represent the number of ligands present. Lastly, if our compound has both a cation and anion, we balance the charges by doing cross multiplication. If the complex ion doesn't have a counter ion, we represent the charge by putting it as a superscript outside the bracket. And that's how you write the chemical formulas of inorganic complexes. The best way to demonstrate what we have learned so far is to do another set of examples. If you want to do the problems yourself, you may pause the video now and unpause once you have written the formulas for the 5 compounds. Our first example is potassium hexacyanidochromate 3. The cation is K+, and the anion has 6 cyanide coordinated to a chromium 3+. We will write the complex anion formula as CrCN6 3-. The charge of the anion is -3 because we have a net charge of -6 for the 6 cyanides and a charge of +3 for the chromium. If we add the +3 to the -6, we get a net charge of -3. We then cross-multiply the charges to get the chemical formula K3CrCN6 for the complex potassium hexacyanidochromate 3. The next example is tris-ethylene diamine cobalt 3 nitrate. Here we have a complex cation and a normal anion. We will write the formula COEN33+ for the complex cation, and the anion will simply be NO3-. We cross-multiply the charges to get the chemical formula COEN3NO33 for the compound tris-ethylene diamine cobalt 3 nitrate. In the third example, we have two different ligands attached to the iron 3+. So in writing the chemical formula, we have to alphabetize the ligands in terms of the first letter of their chemical symbols. We will write chloride first because the C and Cl comes before the O and OH. So the chemical formula is written as FeCl3OH3 3-. The net charge is -3 because the 3 Cl's and the 3 OH's contribute a -6 to the net charge. Couple that with the +3 from the iron 3+, +3 minus 6 gives you -3, which is the net charge of the complex. Since the complex has no counter ion, we will just write it as is with the charge of the complex written as a superscript outside the bracket. The fourth example is diamine tetrachlorido platinum 4. In this example, once again, we have two sets of ligands and we will have to arrange them in alphabetical order. The symbol for the amine ligands is NH3 and the symbol for the chlorido ligands is Cl. So the C and Cl will come before the N and NH3, so we will write the chlorides first, followed by the ammonia ligands. The formula for the compound is PtCl4NH32. The complex is neutral because the -4 charge from the 4 chloride ions is cancelled out by the +4 charge from the platinum 4. In the case of a neutral complex, we do not need to put the charge of the complex outside the bracket. It is understood that the charge of the complex is 0. The last example is tris-ethylene diamine iron 3 hexacyanidoferrate 2. In this example, we have a complex cation and a complex anion. Both the cation and the anion each have one type of ligand, so we do not need to worry about alphabetical order. We write the formula of the cation as FeEN33+. The net charge is +3 because En is a neutral ligand. We write the formula of the anion as FeCN6 4-. The net charge is -4 because the 6 cyanides contribute a -6 to the net charge and the iron contributes a +2 to the net charge. +2 minus 6 gives you -4. And finally, to get the chemical formula of the compound, we cross-multiply the charges to get the neutral compound FeEN34, FeCN63. In this formulation, we have 4 particles with an individual charge of +3 and 3 particles with an individual charge of -4. So +12 minus 12 gives us a net charge of 0, giving the neutral complex FeEN34, FeCN63. And that is it for this set of examples. To summarize, to write the chemical formula of a complex, we write the formula of the cation followed by the anion with no spaces in between. We denote the number of cations and anions by subscripts, which we get by cross-multiplying the charges. To write the formulas for the complexes, we put the formulas inside brackets. We write the formula of the metal first, followed by the formulas of the ligands in alphabetical order, following the first letter of the symbol of the ligand. We also denote the number of ligands present by using subscripts, just like we do for cations and anions. And lastly, if the complex has no counter ion, we denote the charge of the complex as a superscript written outside the brackets. And with that, we have reached the end of the lecture. If you would like to know more about naming inorganic compounds, you may Google the search term IUPAC Red Book. Thank you for watching.